Welcome. Today we're going to talk about a small application of the law of refraction, and this we will see it in the dispersion of light. So we're going to talk about Snell's law. Remember that Snell's law is the law that governs how light behaves when it propagates from the source to destination and undergoes both change in direction and change in medium. I should emphasize that the change in direction is related to or is due to the change in medium. And because light will be undergoing a change in media, we expect, and the different media it propagates in have different indices of refraction. We want to see how light behaves and how a certain aspect of nature is accounted for by these two principles: the idea of an index of refraction and Snell's law. Okay, so a quick recap is that Snell's law is given by this, that is, the angle of incidence is related to the angle of refraction through this relation. That is, it's not direct like with the law of reflection, but rather it's mediated by this trig function together with the index of refraction, where the index of refraction, if you recall, is equal to the speed of light in a vacuum divided by the speed of light in that particular medium. This is a property of the medium, so water will have its own index of refraction, and ethanol will have its own, glass would have its own, diamond would have a different index of refraction. And if we were to reshuffle this formula, we will find that the angle of incidence, the angle of refraction, and here we're assuming that light is moving from medium 1 to medium 2. So therefore the angle of refraction will be given by the arc sine of the ratio of the indices of refraction multiplied by sine of the angle of incidence. That's sine theta 1. So the point here, the takeaway, is that the angle of refraction depends on the angle of incidence. In other words, at what angle is light entering the destination medium? And also, the angle of refraction depends on the indices of refraction. So what objects, what media are we going from, and what medium are we going to also makes a difference. However, so far I have not been fully upfront with you. I have hidden some facts. For instance, I suggested that the angle of, the index of refraction, say for instance water, I claimed that this was 1.333. Well, this is not entirely true. For practical purposes, it is true, but remember, when light is propagating from one point to another, we said it was more profitable and more useful for us to think about it as a ray. However, this does not mean light has lost its wave properties and its particle-like properties. And actually, these properties do show up when light changes media. So the confession is that I need to make is that the index of refraction actually is not all the time the same for all different wavelengths of light. So we might have the same medium, but the amount of the index of refraction for a light of a different wavelength will be different for a light wave of a different wavelength. This is going to be clearer in the next slide, so let's go there. So the takeaway or the confession is that the index of refraction is not the same for all wavelengths of light, even for the same medium. And this table explains it. For instance, water. When light enters water, suppose we had white light, or rather maybe let me say red light. The index of refraction for red light is actually given by 1.331. contrary to what I had suggested over here, and most references are going to suggest. So this doesn't mean this is invalid. It just means we have quoted a particular, an index of refraction for a particular wavelength. So what about orange light? When orange light travels through water, its index of refraction will be given by 1.332, whilst yellow light is going to be 1.333, and green light is going to be 1.335, and so on and so on. The point is, not all wavelengths of light are going to be deflected the same amount. Hence, they're not all going to have the same amount of index of refraction. Or I should say that these values are determined experimentally. Of course, for practical purposes, we might not indicate the index of refraction for all the different wavelengths, but it's worth noting that this is true. Actually, this variation in the index of refraction for the different wavelengths accounts for something we all see after well, not all the time, but after rainfall. It accounts for why we have rainbows, hence the idea of the dispersion of light. So the fact that the different wavelengths of light have different indices of refraction means that different waves will refract differently. That is, they're going to change direction when they enter a medium. They're going to change direction in different amounts. The deflection or their bending is going to be different. Let's look at an example. So let's consider light traveling. We're going to consider two wavelengths of light traveling from a vacuum to water. And we're going to assume that they have the same angle of incidence. So that means they're coming in parallel to one another. Now, red light, when it gets refracted, that is, when it enters water, its index of refraction is given by, for red light, that is 1.331. So its angle of refraction is going to be given by this. We could I've prepared this earlier, but you're welcome to also try it out on your own and verify. The point is that when red light travels from a vacuum and enters water, it's going to be deflected so that it exits, or rather it travels in a water medium at this angle. It came in at an angle of 30 degrees, but when it enters, it gets changed in direction so that its new direction is 22.0649 degrees. That is true for red light. Now, what about violet light? Well, the index of refraction for violet light in water is different from that of red light. What is it? That index of refraction is 1.342, as quoted from this table. 1.342. And if again we were to calculate the new direction of the violet wavelength, the violet light, when it enters water, we're going to find that it enters water and travels through water at an angle of 21.874 degrees, not Celsius, degrees. So notice these two lights, they came in at an angle of 30 degrees, hence they were parallel. But notice upon entering water, they no longer parallel. This is traveling at an angle of 21, this is traveling at an angle of 22. So they're slightly diverging. This diverging or this spreading is known as dispersion. This idea is known as dispersion. Now, in order for you to convince yourself, I would like to give you an exercise. That is, I want you to compare the angles of refraction of orange light to blue light when they propagate from, here I have two cases where both light are propagating, or light waves, they're propagating from a vacuum to diamond. And they both enter the diamond at an angle of 21 degrees. Now, calculate the angle of refraction for the orange light and the blue light and compare. Try to convince yourself that the angles are different, that is, they're going to come in parallel and exit differently, at different angles. I shouldn't say exit, but continue to propagate in diamond at different directions. And perform the exact same comparison, this time not for light traveling from a vacuum to a diamond, but this time for polystyrene or polystyrene. You could compare how the two light rays travel. How much do they change direction? How do they compare once they enter the new medium? And is there, having done these two calculations, or actually it's going to be four of them, what general conclusion can you say? That is, compare how do the shorter wavelength of light, short wave light, let me get that clear. How do these light waves compare when the light wavelength is shorter versus when the wavelength is longer? Remember, blue light has a short wavelength and orange light has a longer wavelength. Now compare, how does wavelength change the angle of refraction? I hope that's clear what I'm trying to get to. And then the answer to this conclusion is going to explain why we have rainbows. You will notice that the different wavelengths, the different colors of light are refracted differently. So give this a try, and if you run into issues, let me know. Okay, we will conclude here. For further reading, I commend the reference that is on our OpenStax book. This is section 25.5. This will fill in all the necessary details that you may have missed. Okay. This idea of dispersion is going to be useful whenever we're talking, it's useful whenever one is designing a lens. You may have heard of chromatic aberration. It's actually related to the fact that the different wavelengths of light refract differently. Okay, I will stop here and we will pick up our next discussion on image formation by lenses, where this idea is going to be important. Okay.